Okay, so welcome to Lab H5 AC Power. In this lab, we're gonna explore a problem that arises when you're hooking up electronic devices to a power grid. Basically, when you hook up an inductor to a power grid, there's a backlog of power, and this is known as the reactive power. This causes interference in the transmission lines and basically ends up wasting energy and money. So to fix this, they use a technique called power factor correction. Basically, just hook up a capacitor in parallel, and that can cancel out the reactive power, and it ends up supplying current to the load when the inductor fails to do so. Um, this makes it so that there's practically no interference, and you end up saving energy and money. So in this lab, we're going to explore how to do this. Um, so this is our circuit. This is the load network on the right hand side. We have our inductor here, and then RL just represents the internal resistance for the inductor. R5 is 10 ohms, and we made it small just so that it can represent the transmission line resistance. We have AC power and then a parallel component of resistors. So we can start by solving the circuit analytically. Um, we just start by finding the impedance, and then we can use this formula to find the power factor, which is 0.48. Um, this means that the AC current is supposed to lag behind the AC voltage, and that's what we expect. Uh, Once we hook up the capacitor, we want this to be equal to 1, which means that it's going to be dissipating constant power. Then we use a voltage divider to find V load, and then we can use these commands to find the imaginary and the magnitude and the phase of it. And then we can use Ohm's law to do the same thing with the current. Then we can find our load voltage phase, divide it by its angular frequency, and then get its individual phase shift. So theta z is positive, which means it's a lagging inductive load, and that's what we expect. We can use this formula to find the power, and then just take the imaginary part of it, and that is the reactive power. So right now it's positive, which means there's a backlog of power, and it's causing interference. So once we hook up the capacitor, we expect this to be equal to 0. So then we can do the power factor correction technique. We use admittance formulas to find the correct capacitance. We found that it was 189 nanofarads, so we had to change up the circuit so that we could use this 36 nanofarad capacitor in the physical build because that's what we have. So we just had to change up the frequency pretty much. We just do the same steps as we did above, and to solve this circuit and get the values that we want, and then we can hook up the capacitor that we want, and we expect that the reactance goes to 0, and anything that has to and the phases should be aligned. So anything that has to do with phase should be equal to 0, and that's what we got. And the only thing we did different in this was that we just changed up the impedance because the capacitor is now connected. So you can see that these are the values from before we did power factor correction, then after. So the reactive power is 0, which is good. So capacitor did its job and canceled out the reactive power. And since the phase shifts are 0, we know that the power factor is equal to 1, which means that it's constantly dissipating power. Then we have our multism solution. We hooked up the ground here to the ground, and then channel 1 is just measuring the source voltage. Channel 2 is measuring across the transmission line resistance. And so we can get our amplitude for the transmission line resistance here, and then our time difference between the two voltages. We're going to use the time difference here and then the amplitude over there. We're using a voltage phasor to solve this right now. Basically, we're just going to use these formulas to find the same values as we did before. So you can see here that we have our power factor is P average over P apparent. These are and since we've already solved for the power here, we can just use these definitions to find the power factor. And so we found that the power factor is equal to 0.2, which is similar to what we got analytically. And then our Q is 0.002. And what we want is that this again should go to, once we connect the capacitor, we want this to go to 1, and then this should go to 0. And we do the same thing here. You can see that the the waveforms are now in phase. So, and we got that the reactive power is equal to 0 and our power factor is equal to 1. So now we know that it's constantly dissipating power. And this is just a table that's comparing them. We did the same thing in our physical build as we did in multisim. So this is our positive, this is our physical build, this is the positive terminal, this is the ground. It just basically goes from left to right, the same way as the circuit was built in multisim. And we hooked up the grounds over here, and then basically just the same way as we did it in the multi-sim solution. Um, so we're getting similar. This is the waveform generator from the Handtech, and we're getting similar graphs and similar values. And we use the same calculations as we did in multi-sim for this. And then we hook up our capacitor here in the top left, and then we should expect that the phase difference is non-existent. Um, and then we do our same calculations, and the values we got were, so this is prior to power factor correction, and then this is after. So the reactance goes to the reactive power goes to 0, and then the power factor is 1. And we got similar values as we did from the multi-sim solution. And we did have some error, and the cause for this error was probably, one, it was probably due to that just cursor placement on the Handtech, and then the uncertainty that we've calculated here from the passive components. And yeah, so that is our lab on AC power and power factor correction. Thanks.